In this video, we are combining the idea of area vector and density. More specifically, electrical field line density. So that is with the help of electric flux. First, let's understand the word flux. Flux is a measure of how much something is passing through a given surface. So wherever area vector is used, even flux, the idea of flux is used. So all the things that we listed over there, right? Anything to do with fluids, anything to do with heat, magnetic field, electrical field, so on and so forth. So all of those places we use the idea of flux. So what is flux? Flux is a measure of how much something is passing through a given area. As simple as that. So what is electrical flux then? Electrical flux is a measure of measure of the number of electrical field lines passing through a given surface. Actually, I missed a keyword. Normally. That is perpendicular. Right? So let me explain it this way. So we have something like this over here, and this is something like this. Now, when we compare, this flux is clearly more than this flux because the areas are same. The number of field lines passing through on the first is more than that of the second. As simple as that. If these lines are electric, then it's electric flux. That's it. Okay. Let's look at the mathematics. So we are going to represent it with obviously delta flux with regarding to electric field, right? And then we're looking at normal component only. And multiply that with the area vector or surface area. So how do you find a normal component of something? So we make use of correct cos theta. So let me write it over here. If this is surface, this is the field line falling on the surface. This is theta. And this would be your theta again. And this will be your E cos theta. I should have done a better job, but that's the space I have actually. Let me increase the space also. Okay, let me redo that. So let's look at an area. Then this is your, that's your electrical field. Now that's your normal, that's your theta. And again, I need some space. So if I have the line to be something like this, and if this angle is theta, why is that theta again? These two are parallel, this two acts like an alternative interior angle, is it not? So this angle should be equal to this angle. This and this has to be equal. So when we resolve it, so we'll get two of it, two components, that is. So clearly this is opposite, this is adjacent. So if this is E, this will be E cos theta, provided this is E. And you can see with respect to the surface, this is correct, normal. Okay, guys. And so this would be a flux, electrical flux in this case is E cos theta, and surface area is your delta S or S, whatever you guys want to call it as. What does this look like? Yes, it is a dot product. And that's your formula. A very simple formula. We have other version wherein you have your integration as well. Same funda. Now, what is the SI unit? What do you think will be the SI unit? It will be Newton per Coulomb meter. Is that correct? Wrong. It is meter cube. Right? Again wrong. It is meter square. Dimension, well, you guys do it. Kind of bored. So is it scalar or vector? It's a dot product. So it has to be scalar. Okay, guys. So finally, let's understand. Let me use this space. So we are trying to understand how charge or a charges or line of charge affect a space. Affects a space. We make use of something called as electrical field lines to make it easy. Now when it comes to lines, right, and surface, so we have electrical field line density, and surface we have something called as area vector, right? So combining these two, we have something called as flux. So flux has to do with the number of field lines that are normal to the given surface, which is passing through it, and normal. More the normal, stronger the field strength. Stronger that area will feel the strength. I think my language is not right, but you guys got it now. So more the perpendicular, stronger it is. That's what I meant. So mathematically, we are taking that aspect into account. Normal component of, it can be any field. In this case, it's electrical, into the surface area. Makes sense. Again, we're looking at total. The surface area need not be 1. It can be any length, actually not length, any area, any amount of area. And we get a cost component, thus making it a dot product. So since it's a count, 1, 2, 3, 4, 5, 6, it's count, right? It has to be a scalar quantity, and also the formula tells it's a scalar quantity. The SI unit is Newton per Coulomb meter square. Dimension is something that I want you guys to derive it out. So yeah, that's it.